Imagine a still pond on a clear summer day. The surface is smooth like glass, reflecting the azure sky above. Just as the pond's surface can be disturbed, creating ripples that spread outward, the microscopic world of atoms and particles is governed by waves of probability. These waves, described by the famous Schrodinger wave equation, hold the key to understanding the strange and counterintuitive behavior of matter at its most fundamental level. The Schrodinger equation provides a way to calculate the probability of finding a particle, like an electron, at a particular location in space at a specific time. Let's return to our tranquil pond. Now imagine tossing a small pebble into the center. The impact creates a disturbance, sending out ripples that spread across the surface. In the quantum world, the Schrodinger equation describes a similar phenomenon, but instead of ripples of water, it describes waves of probability. These probability waves, also known as wave functions, are not directly observable. The square of the amplitude of the wave function at a particular point in space gives us the probability of finding the particle at that location. Just as the ripples on the pond spread out and lose intensity, the probability of finding a particle far from its initial position decreases over time. The Schrodinger equation provides a mathematical framework for understanding how these probability waves evolve over time. By solving the equation for a given set of conditions, we can predict the behavior of quantum systems with remarkable accuracy. While the mathematical details of the Schrodinger equation can be complex, the underlying concepts are surprisingly intuitive. The equation essentially describes how the wave function of a particle changes over time. It tells us that the rate of change of the wave function is determined by the particle's energy and the forces acting upon it. Think of the wave function as a map of the particle's possible locations. The higher the peak of the wave at a particular point, the greater the probability of finding the particle there. As the particle moves and interacts with its environment, its wave function evolves, and the map of probabilities changes accordingly. From the energy levels of atoms to the behavior of semiconductors and electronic devices, the Schrodinger equation has revolutionized our understanding of the microscopic world. One of the most bizarre aspects of quantum mechanics is the concept of superposition. Unlike classical objects that exist in definite states, quantum particles can exist in a combination of states simultaneously. This is analogous to our pond ripples, where multiple ripples can overlap, creating complex interference patterns. Imagine dropping two pebbles into the pond at slightly different locations. The resulting ripples would interfere with each other, creating regions of high and low amplitude. Similarly, a quantum particle can exist in a superposition of states, meaning it is in multiple states at once until a measurement is made. This superposition principle leads to the famous thought experiment of Schrödinger's cat, where a cat in a box is both dead and alive until the box is opened and an observation is made. Another strange consequence of quantum mechanics is Heisenberg's uncertainty principle, which states that it is fundamentally impossible to know both the position and momentum of a particle with perfect accuracy. The seemingly bizarre world of quantum mechanics, governed by the Schrodinger equation, is not just a theoretical curiosity. It has led to revolutionary technologies that have shaped our modern world. One of the most well-known applications is the laser, which relies on the quantum mechanical behavior of light and matter. Lasers work by exploiting the energy level transitions of atoms. By exciting atoms to higher energy levels and then stimulating them to emit photons in a coordinated manner, lasers produce highly focused beams of light with unique properties. These properties have led to countless applications, from barcode scanners and fiber optic communications to laser surgery and advanced manufacturing techniques. Another groundbreaking application of quantum mechanics is the transistor, the building block of modern electronics. Looking towards the future, quantum computing holds immense promise, with the potential to solve problems that are intractable for classical computers such as drug discovery, materials science, and cryptography. The Schrödinger equation, despite its mathematical complexity, has opened our eyes to a strange and counterintuitive realm where particles behave like waves and uncertainty reigns supreme. By using simple metaphors, like the ripples on a pond, we can begin to grasp the profound implications of quantum mechanics. These metaphors help us visualize the invisible world of atoms and particles, making the abstract concepts of wave functions, superposition, and uncertainty more accessible. Understanding quantum mechanics is not just an intellectual pursuit, it is crucial for advancing technology and addressing some of the most pressing challenges facing humanity.